In this lesson, we're going to dive into the topic of radioactive decay half-life. We'll go over two different ways of solving half-life problems step by step. This video is packed with practice questions and detailed explanations to help you master this concept with confidence. And to take it a step further, we will tackle a realistic MCAT-style passage all about radioactive decay half-life. We will break down the analysis and explanations for each question in detail. Let's jump right in and let's get started. Here we're going to define the half-life of a radioactive isotope. As we have learned before, some atomic nuclei are unstable. They do not like to stay the way they are, so they undergo radioactive decay to turn into another element or a more stable form of themselves. And the time it takes for this decay to happen can be really different depending on the isotope. This is where the term half life comes in. Half life is just a fancy way of saying the time it takes for half of a radioactive substance to decay into something else, either a different element or a more stable version of itself. Now, let's explain the graph you see in front of you in more detail. On the y-axis, we have the amount of substance, and on the x-axis, we have the time. Look at the bars. Each one is exactly half the size of the bar before it. This shows us that a certain amount of time passes before the substance is reduced by exactly one half. So the substance starts at a high concentration or amount, and after the passage of each half-life, its amount gets cut in half. All half-life questions on the MCAT follow a first-order kinetic rate law. This is important for half-life calculations. Just to give you some perspective, not all nuclei are the same. For example, francium 223 has a half-life of about 22 minutes, while potassium 40 it sticks around for 1.25 billion years. Let's now talk about how to calculate half-life. There are actually two ways we can use to calculate half-life. The first way is by using logic and intuition. Basically, you reason it out conceptually. This method can save you a lot of time on the MCAT, especially when the question is testing your understanding rather than solving some mathematical variable. The second way is the more formal, more precise method, which uses an equation to calculate half-life. The second method uses the equation shown on this slide. The equation is AF is equal to AI multiplied by e to the power of negative k times t. This equation tells us that the radioactive decay in this case follows a first order kinetic rate law. AF or A final is the final amount of the substance after some time has passed. AI or A initial is the initial amount of the substance. E is the base of the natural exponential function, which has a value of approximately 2.71828. T represents the time elapsed, and K is the decay constant, which has its own equation. And that equation equals ln2 divided by T1 half. Here, ln2 is the natural log of 2, which equals about 0.693. We use ln2 because all decay processes on the MCAT follow a first order rate law. T1 half is equal to the half-life. Now notice that there is a negative sign in front of the k times t. That negative sign tells us that we are dealing with a decay process, meaning that the amount of substance is decreasing over time. One thing to keep in mind, T1 half stands for half-life, while T in the main equation stands for time elapsed. They are not the same thing. T1 half is a constant that tells you how long it takes for half of the sample to decay. And T is just the amount of time that has passed or elapsed. We're going to use both methods so you can see how each one works. Depending on what the MCAT question is asking, you can use whichever approach gets you to the correct answer the fastest. Alright, now let's put everything we've learned in action with a few practice problems. Just a quick note, the numbers I'm about to show you are not real half-life or time values. They are just presented here for practice purposes, so you can focus on understanding the concepts and the steps. Let's dive in. Let's start by solving some problems using the first method, the intuitive or the conceptual approach, which does not require using the equation. So question number 1 reads, lead 210 Pb210 has a half-life of 10 days. If the initial sample has a mass of 400 grams, answer the following. A. How much of Pb210 will remain after 50 days in grams? What percentage of the original sample will remain in after 50 days? And C says what fraction of the original sample will remain after 50 days. Now let's reason our way to the correct answer. First, we need to figure out how many half-lives fit into 50 days. From the question, we know that this substance has a half-life of 10 days. So to find out how many half-lives are in 50 days, we simply need to divide 50 by 10, which gives us 5. That means 5 half-lives have passed in 50 days. Next, let's figure out how much of the substance remains after those 5 half-lives. Let's start with option A. We begin with an initial amount of 400 grams of lead. Each arrow on the diagram for part A here represents the passage of one half-life, and each half-life reduces the amount by exactly one half. After the first half-life or 10 days, 400 grams of the substance becomes 200 grams. After the second half-life or 20 days, 200 grams becomes 100 grams. After the third half-life or 30 days, 100 grams becomes 50 grams. After the fourth half-life or 40 days, 50 grams becomes 25 grams. And finally, the fifth half-life or 50 days, 25 grams becomes 12.5 grams. So after 50 days or 5 half-lives, the final amount remaining is 12.5 grams. This shows that with every half-life that passes, the original amount of the substance is reduced by one half. Now for option B, it is asking us to express the amount of substance remaining as a percentage value. To solve this intuitively without using the formula, there are two ways to get the correct answer. The first way is by using the diagram shown on this slide for option B. We'll start by setting the initial 400 grams equal to 100% at the beginning of the decay process. Now let's go through each half-life step by step. After the first half-life, that 100% is reduced to 50%. After the second half-life, 50% becomes 25%. After the third half-life, 25% becomes 12.5%. And after the fourth half-life, which is 40 days, 12.5% becomes 6.25%. And finally, after the fifth half-life, or 50 days, 6.25% becomes 3.125%. So after 5 half-lives, only 3.125% of the original substance remains. The second way to find the same answer conceptually is by using the initial and the final masses of the substance. We already know that the final amount is 12.5 grams and the initial amount is 400 grams. So we divide 12.5 by 400 and then multiplying that by 100, it gives us a percentage value, which equals 3.125%. This matches our first result. Therefore, the answer to part B is 3.125%. Option C is asking us to express the amount of substance remaining as a fraction. Remember, the substance is reduced by one half with each half-life. So to find the fraction remaining, we multiply one half by itself 5 times, because the original amount goes through 5 half-lives. So when we multiply 1/2 by itself 5 times, we get a value of 1 over 32. When we divide 1 by 32 and then multiply that one by 100, we get 3.125%, which matches our answer from option B. So the fraction of the substance remaining after 5 half-lives is 1 over 32 or 3.125% of the original amount. On this slide, we're going to go over the second method of solving half-life problem. On the left side of the slide, you can see the values that are given to us by the question stem. The initial amount, or AI, is equal to 400 grams. The half-life, or T1 half, is equal to 10 days. The time elapsed, or T, is equal to 50 days. The formula that we're going to be using is AF is equal to AI multiplied by e to the power of negative k times T. To find the decay constant, we'll use the equation K is equal to ln2, which has a value of 0.6931 divided by T1 half, or the half-life. We know that the half-life has a value of 10 days. So for step number 1, we need to find the value of K. We divide 0.93 by 10, which gives us K is equal to 0.0693. Once we have our value for K, we move on to step number 2, which is to substitute all the values into the main equation. So AF is equal to 400 times e to the power of negative 0.0693 times 50. The negative sign in the exponent comes from the original equation, and it indicates that this is a decay process, meaning the amount of the substance is decreasing over time. And remember, the 50 here represents time elapsed, not the half-life. These two are two different values. Now for step number 3, let's solve the equation. When we plug everything into the calculation, we get a final amount of 12.52 grams. So after 50 days, the amount of substance remaining is about 12.5 grams. This matches very closely with the value we obtained earlier using the intuitive method. Now let's move on to option B, which asks about the percentage of the substance remaining. All we need to do here is divide 12.5 grams by 400 grams, then multiply by 100, which gives us a value of 3.125% remaining. For option C, we are looking for the fraction of the substance remaining. Since the sample goes through 5 half-lives, we multiply 1/2 by itself 5 times, giving us 1 over 32. If we divide 1 by 32 and then multiply that by 100, we get 3.125%, which matches our percentage value from option B. So the fraction of the substance remaining after 50 days is 1 over 32. Now that you know how to solve half-life problems both intuitively and mathematically, on the next few slides, I'm going to provide you with more questions. You should try these questions on your own using both methods before we go over the solutions together. Let's give them a try. Here's question number 1. The final amount of cesium-137, CS-137, is 20 grams after it has decayed. Cesium-137 has a half-life of 50 minutes. What was the initial amount of cesium-137 if 200 minutes passed during this decay process? This question is asking us to determine the initial amount of the substance before it began its decay process. Let's go through the solution step by step. The information given is listed on the top right side of this slide. According to the question stem, the final amount of the substance after decay is 20 grams. The time elapsed is 200 minutes. The half-life T1 half is 50 minutes. Our first step is to figure out how many half-lives pass in 200 minutes. To do that, we divide 200 by 50, which gives us 4. This means 4 half-lives have passed for cesium-137 to decay to a final amount of 20 grams. We can solve this problem intuitively using the conceptual method, which is often the fastest way. Here, we're given the final amount and asked to find the initial amount. That means we're moving backward in time. So instead of dividing by 2, we need to multiply by 2 for each half-life. Let's start with the final amount of 20 grams. After moving back one half-life, 20 times 2 is 40 grams. After 2 half-lives, 40 times 2 is 80 grams. After 3 half-lives, 80 times 2 is equal to 160 grams. After 4 half-lives, 160 times 2 is equal to 320 grams. So the initial amount of cesium-137 is 320 grams. Because we are moving backward in time, we multiply by 2 each time instead of dividing by 2. We do this 4 times since 4 half-lives have passed. Now we can also use the mathematical method to solve this question as shown at the bottom of the slide. We need to use the decay formula to get the initial amount. Before we can use the formula, we need to find K in step number 1. The formula for K is equal to ln2 divided by T1 half or the half-life. We know that ln2 is equal to 0.693 and the half-life is 50 minutes. So K is equal to 0.693 divided by 50, and that gives us a value of 0.01386. In step number 2, we need to substitute our values into the decay equation, and that gives us 20 is equal to AI times E to the power of negative 0.01386 times 200. In step 3, we solve the initial amount, so multiplying the superscripts, we get 0.01386 times 200. That is equal to 2.772. We need to raise e to the power of negative 2.772, and that equals 0.0625. To find the initial amount, we need to divide both sides by 0.0625. Once we do that, we get 20 divided by 0.0625. This equals the initial amount, and the value equals 320 grams. So using both the intuitive method and the equation method, we find that the initial amount of cesium-137 is 320 grams. Let's move on to question number 2. So question number 2 is asking us, it takes 460 minutes for radium-226, Ra-226, to decay to 1/8 of its original amount. What is the value of the decay constant K? Take a minute to solve this problem on your own and then come back to see the solution. Here's the solution to question number 2. Here we are given some information and asked to find the value of the decay constant K. The information provided is as follows. The fraction of the substance radium Ra-226 remaining is 1/8, meaning only 1/8 of the original amount remains after a certain amount of time. The time elapsed is equal to 460 minutes, and we also need to determine the value of K. There are several ways to solve this problem, but let's follow the method outlined on this slide. In step number 1, we need to identify the formula that we will be using. The formula for the decay constant is equal to K is equal to ln2 divided by the half-life. In step number 2, we need to determine the number of half-lives. If only 1/8 of the original amount remains, we can find that the number of half-lives that have passed by multiplying 1/2 by itself 3 times until we get a value of 1/8. So multiplying 1/2 by itself 3 times gives us a value of 1/8, which means 3 half-lives have passed. In step number 3, we need to find the duration or the length of the one half-life in minutes. To do that, we need to divide the total time elapsed, which is 460 minutes, by the number of half-lives, which is 3. When we do that, we get a value of 153.3 minutes. Now, in step number 4, we need to substitute the values into the decay constant formula. To get K is equal to 0.693 divided by the half-life in minutes to get 0.00452 per minute. The decay constant of radium-226 is 0.00452 per minute. Let's move on to question number 3. Question number 3 asks, if after decay the amount of barium remaining is 1/16th of its original amount and the decay constant K is 0.6 per hour, what is the elapsed time? Here's the solution to question number 3. This question is asking us to find the time elapsed. Now, I want you to know that there are different ways to arrive at the correct answer using the equations and the formulas we discussed. In this example, we will use one of those methods, just to keep the video at an appropriate length. You can solve this problem either by using the half-life formula or by using the decay constant formula, which does not require the use of natural logs or ln. So let's go over how to solve this question step by step. From the question stem, we are told that the amount of substance remaining as a fraction is 1/16. The decay constant K equals 0.6 per hour, and we are asked to find the time elapsed. In step number 1, we need to use the decay constant formula, which is K is equal to ln2 divided by the half-life. In step number 2, we need to determine the number of half-lives. We know that each decay process reduces the amount of substance by 1/2. To reach a remaining fraction of 1/16, we multiply 1/2 by itself until we reach that value of 1/16. So 1/2 multiplied by itself 4 times gives us a value of 1/16, meaning that for this time frame, 4 half-lives have passed. In step number 3, we have to rearrange the formula for the half-life. We know that the decay constant formula is K is equal to ln2 divided by the half-life. If we rearrange this equation, we can solve for the half-life. T1/2 or the half-life is equal to ln2 divided by K. In step number 4, we need to substitute known values into the half-life formula. So T1/2 is equal to 0.693, which is the value of ln2 divided by 0.6 per hour, which is a decay constant value that was given to us in the question step. When we solve this, we get 1.155 hours. So the half-life of the substance is 1.155 hours. In step number 5, we can use the half-life to calculate the total time elapsed. So to find the total time elapsed, we multiply the length of one half-life by the number of half-lives, which is 4 in this case. The total time is equal to 4 times 1.155, and that value equals 4.62 hours. So a total of 4.62 hours have passed, leaving only 1/16th of the original substance remaining. Let's move on to question number 4. Question number 4 asks, in 35 days, a 520-gram sample of strontium undergoes alpha decay, leaving a final amount of 16.25 grams. What is the half-life of this sample in days? Here's the solution to question number 4. The question then provides us with some information which we will list here. It tells us that the initial amount of the substance is 520 grams and the final amount is 16.25 grams. It also tells us that it takes 35 days for the substance to reach that final amount. We are asked to find the duration or the length of one half-life in unit days. We will solve this problem using our intuitive or the conceptual approach, which can save us a lot of time on the MCAT exam. So for the first step, we need to figure out the number of half-lives. Each half-life cuts the original amount by 1/2. So we need to divide each amount by 1/2 to reach the final amount. The first half-life cuts the original amount in half, so we divide 520 by 2 to get 260 grams. During the second half-life, 260 is divided by 2 to give us 130 grams. In the third half-life, 130 is divided by 2 to give us 65 grams. In the fourth half-life, 65 is divided by 2 to give us 32.5 grams. And finally, in the fifth half-life, 32.5 is divided by 2 to give 16.25 grams. So as you can see, it takes 5 half-lives for the substance strontium to decay to a final amount of 16.25 grams. In step number 2, we need to determine the length or duration of one half-life. To find the duration of a single half-life, we divide the total time elapsed by the number of half-lives. So 35 days divided by 5 half-lives is equal to 7 days. Therefore, the length of one half-life is 7 days. All right, let's jump into the final question, number 5. The final question says I-131 is used as a tracer for the thyroid gland in medical imaging. I-131 has a half-life of 10 days. If a patient drinks a sodium iodide solution containing I-131 on a Friday, how many days will it take for the concentration of I-131 to decrease to 6.25% of the initial concentration? Is it 11 days, 20 days, 48 days, or 40 days? Here's a solution to number 5. In this question, we are asked to find the total time elapsed. Now, notice something interesting here. Sometimes the MCAT likes to include extra or irrelevant information just to test your focus. And that's exactly what is happening here in this question. The stem tells us that the patient drank the sodium iodide solution on a Friday, but that detail has no impact on the calculations we need to make. Always remember, stay focused on what the question is actually asking. Don't let irrelevant information throw you off. Now let's answer this question. In step number 1, we need to determine the number of half-lives. Let's use our conceptual approach to solve this half-life problem. We can use the arrow diagram to better help us find the answer. We are told that the final concentration of iodide solution is 6.25% of the original amount. So we need to start with 100%. After the first half-life, that 100% drops to 50%. After the second half-life, it drops to 25%. After the third half-life, it is reduced to 12.5%. And after the fourth half-life, it is 6.25%. So it takes 4 half-lives for the concentration to drop from 100% down to 6.25%. In step number 2, we need to determine the total time elapsed. So to find the total time elapsed, we simply need to multiply the number of half-lives by the length of one half-life. So that is 4 times 10 days per half-life, which is equal to 40 days. So the total time elapsed is 40 days, which means option B is the correct answer. So before we start the next section, I want to make sure that you're mentally ready to tackle it. I'll give you a few quick tips for solving half-life problems on the MCAT. First, always start by asking what the question is actually asking you. Most MCAT half-life questions can be solved using the conceptual method, which we use the arrow diagram. This method is fast and gives you a reliable ballpark answer, which is exactly what you need on the exam. With that said, know the key formulas I showed you in this video in case a problem requires you to use them. The MCAT, though, rarely asks you to do heavy math. If you find yourself doing more math than necessary, stop and rethink your approach and switch to a more conceptual approach. Before we move on, review everything you have learned so far. Remind yourself that you already know the background science needed to solve most Half Life problems. If you need more practice, pause this video and work through more Half Life problems before continuing. In the next section, I will present a realistic MCAT style passage to you. When you read the passage, focus on finding the main idea. If the passage throws a lot of detail at you, don't get stuck on the small facts. Note where they are so you can come back to them later. Look for relationships in the passage and jot them down. Now I'm going to read the passage and the questions to you. Take some time to read the passage on your own and try the questions on your own. Then we will go over a full passage analysis and the solutions together. Good luck, let's begin. Positron emission tomography is a technique used for medical imaging. A PET scanner detects gamma photons that are produced when a positron annihilates with an electron. In this study, scientists use scandium-44, SC44, as a radioactive tracer attached to the Fab region of cetuximab. Cetuximab is a monoclonal antibody that binds to the epidermal growth factor receptor EGFR. It has been observed that many tumor cells express elevated levels of EGFR or its corresponding gene. The Fab region, or the antigen binding portion of cetuximab, was digested using the enzyme papain. The Fab fragment, along with a bifunctional chelator known as CHX-A-DTPA, was then bound to SC44. This three-component 5-tracer complex enables high-quality PET imaging of internal organs and tumors. SC44 is produced in a cyclotron by irradiating calcium-44 with protons through the nuclear reaction shown. SC44 has a half-life of approximately 3.9 hours, which is ideal for completing PET imaging procedures. It does not remain in the bloodstream for long. After injection of the three-component tracer, scientists were able to track its distribution across various body tissues, as shown in Figure 1. The term percent ID per gram represents the percentage of the injected dose per gram of tissue, a measure of how much tracer accumulates in specific region. Figure 1. Tracer accumulation in body tissues. Question number 1. In this study, it is mentioned that the Fab tracer, scandium-44, SC44, is produced by irradiation of calcium-44 with a proton. Which of the following represents the correct nuclear reaction for this process? Question number 2. A patient is injected with 25 grams of scandium-44 bound to the Fab SHX-A-DTPA complex. Approximately how long will it take for the sample to decay to 5 grams? Question number 3. The Fab tracer includes a binding site that allows attachment to EGFR. Based on Figure 1, why does the percent ID per gram value remain elevated in kidney tissue compared to other tissues? Answer choice A says kidney cells express the highest level of EGFR. Answer choice B says kidney cells have a higher binding affinity for SC44 than other cell types. Answer choice C says kidney cells process the tracer to enable its clearance from the body. Answer choice D says kidney cells have a higher affinity for CHX-A-DTPA. Question number 4. In a follow-up experiment, scientists used different isotope of scandium Sc that undergoes alpha decay. They repeated the procedure to perform a PET scan, successfully binding this new scandium isotope to the Fab region of cetuximab and the SHXA-DTPA chelator to form the same three-component tracer complex. However, after injecting this tracer into a patient, no binding of the Fab region to its target receptor was detected. Which of the following provides the most reasonable explanation for this observation? Answer choice A. Says the Fab region of the antibody was denatured prior to injection, preventing it from properly binding to EGFR. Answer choice B says the Fab fragment was not effectively digested by the enzyme papain, preventing the new SC isotope from binding correctly to the Fab region. Answer choice C says the new scandium isotope had a shorter half-life of approximately 3.1 hours, providing insufficient time to perform a PET scan. Answer choice D the new scandium isotope underwent alpha decay, and the resulting decay products were undetectable by the PET imaging. Question number 5. Within liver tissue, what type of nuclear decay does scandium 44 undergo that allows it to be detected by a PET scanner? Answer choice A says beta plus decay. Answer choice B, gamma decay. C, alpha decay. D, beta minus decay. Here's the passage analysis. So on this slide, we will go over the passage analysis. On the MCAT, your notes should not be too extensive. Sometimes just writing one or two words is just enough. You only need to write enough to help you identify key information that brings you closer to the main idea of the passage. Every person takes notes differently, and which is completely fine. And on this slide, I'm going to present to you the kind of notes that I would take if I were to take the actual MCAT exam. What you should pay attention to is the structure of the passage. You should also note any science background information that you have learned before, recognize any relationships or comparisons, and of course, identify the main idea of the passage. So let's start. The first sentence reads positron emission tomography PET is a technique used for medical imaging. When you read this first sentence, a few things should come up to your mind. You should start forming a general idea of what the rest of the passage will discuss. Just from the phrase positron emission tomography, even without reading further, you can already predict that the possible direction of the passage would be. It might discuss radioactivity since it mentions positron. It may explain how a PET scanner works. It may describe how internal organs are analyzed, or it may outline some medical conditions that require PET scans. You do not need to write all these ideas just to think about them mentally. It would help you focus your attention on what to expect next. The second sentence says a PET scanner detects gamma photons that are produced when a positron annihilates with an electron. This sentence is packed with background science information that you've likely encountered before. It mentions radioactive decay, gamma photons, and positrons, which is all the physics concepts that we have studied before. You should highlight this sentence and be ready in case a question later asks about them. The next paragraph says in this study, scientists used scandium 44, SC44, as a radioactive tracer attached to the Fab region of cetuximab. Cetuximab is a monoclonal antibody that binds to the epidermal growth factor receptor, EGFR. It has been observed that many tumor cells express elevated levels of EGFR or its corresponding gene. When you read this paragraph, you should recognize that the passage is shifting focus to the tracer used in the PET scan. Since scandium 44 is introduced here, make sure that you highlight it. This paragraph introduces new information, so note where they appear. The next paragraph says the Fab region or the antigen binding portion of cetuximab was digested using the enzyme papain. This fab fragment, along with a bifunctional chelator known as the CHXA-DTPA, was then bound to SC44. This three-component fab tracer complex enables high-quality PET imaging of internal organs and tumors. SC44 is produced in a cyclotron by irradiating calcium 44 with protons through the nuclear reaction shown. This next paragraph goes into more detail about how the tracer was prepared for PET imaging of internal organs. It contains a lot of detailed information, but the key point here is still scandium 44 because it is repeatedly mentioned, so you can predict at least one or two questions will be about this isotope. The paragraph also hints at a nuclear reaction, which is not in a form that is very familiar, so be alert about a question that will test your understanding of it. The final paragraph says scandium 44 has a half-life of approximately 3.9 hours, which is ideal for PET imaging procedures. It does not remain in the bloodstream for long. After injection of the three-component tracer, scientists were able to track its distribution across various body tissues, as shown in Figure 1. The term percent ID per gram represents the percentage of the injected dose per gram of tissue, and which is a measure of how much tracer accumulates in a specific region. The final paragraph again provides more information about scandium 44, confirming that this isotope is central to the passage. Since we just studied half-life, take note that this concept may appear in one of or two questions. So, on your first read, you don't need to thoroughly analyze the figure. Just read the caption to understand what the figure is showing. If a question asks about the figure, you can return to it and then analyze it in more detail at that point. The main idea of the passage is that it describes the radioactive tracer used in positron emission tomography and how it functions in imaging studies. Let's move on to question number 1. Question number 1 asks, in this study, it is mentioned that the Fab tracer scandium 44 is produced by radiation of calcium 44 with a proton. Which of the following represents the correct nuclear reaction for this process? The passage mentioned scandium 44 multiple times, and we predicted that one of the questions would ask about this isotope. And the first question asks us to write a balanced nuclear reaction that produces scandium 44. The passage provides a reaction for making scandium 44, but it is written in an unfamiliar form. Let's use what we know about nuclear reactions to pick out the correct answer. From our prior knowledge, we know that every nuclear reaction must conserve both atomic number and mass number on both sides of the equation, or both sides of the reaction. We can use this rule to eliminate wrong answer choices. Starting with option A, both atomic numbers and mass numbers are balanced. However, the option produces scandium 45 instead of scandium 44, which was stated in the question stem. So option A is not right. In option B, the total mass number on the reactant side is 44 plus 1, which equals 45. But scandium 44 has a mass number of 44 on the product side. Because the mass numbers do not match, option B is wrong. Option C incorrectly represents a proton. A proton has a mass number of 1 and an atomic number of 1. But this option shows the wrong values, so option C is not right. The only option that conserves both the atomic number and the mass number is option D. This reaction includes a neutron as a product, which balances the mass numbers perfectly. While we may have never seen a reaction that emits a neutron, this is completely valid. As long as we apply what we have learned before, we can confidently identify the right answer choice. So the correct answer is D. As you can see, this question was not difficult at all. It may have been presented in a slightly obscure way, but if you stay grounded in the basic concepts and trust what you have already learned, you will find the correct answer choice becomes clear almost every time. So, with that mindset, let's move on to question number two. Question number two says a patient is injected with 25 grams of scandium 44 bound to the Fab SHXA, the chelator complex. Approximately how long will it take for the sample to decay to 5 grams? This is a very straightforward problem that asks us to solve a half-life problem. The question provides the initial amount of the sample, and we are asked to determine how long it takes for that sample to decay to a final amount of 5 grams. The passage states that the half-life of the sample of scandium 44 is 3.9 hours. We will use the conceptual method which uses the arrow diagram to solve this problem. So we need to start with the 25 grams of scandium 44. After the first half-life, the amount is reduced to 12.5 grams. After the second half-life, it decreases further to 6.25 grams. And after the third half-life, it becomes 3.125 grams. Since the final amount given in the question stem is 5 grams, this value lies between the second and the third half-lives, and it is much closer to the second half-life. On the MCAT, we typically don't need to calculate exact values, and approximate or ballpark values is just sufficient, especially since the answer choices here use the word about. So to estimate the total time elapsed, we multiply the number of half-lives by the length of one half, or 3.9 hours. Because we do not have a calculator on the MCAT, we can round 3.9 to 4 hours for easier estimation. So for 2 half-lives, 2 times 4 is equal to 8. And for 3 half-lives, 3 times 4 is equal to 12. Since 5 grams lies between 6.25 grams and 3.125 grams, the total time elapsed should be between 8 and 12 hours. It should be a little bit closer to 8 hours. Therefore, the best answer choice is option B, or about 9 hours. So here's question number three. It reads the Fab tracer includes a binding site that allows attachment to EGFR. Based on figure 1, why does the percent ID per gram value remain elevated in kidney tissues compared to other tissues? So this question refers to figure 1, which shows how much of the tracer measured in percent ID per gram, or percentage of the injected dose per gram of tissue, is detected in different body tissues over time. So even though the tracer binds to EGFR, the passage does not mention how much EGFR each tissue expresses. So let's quickly go through the options. In option A, it is stated that the kidney cells express the highest level of EGFR. This is wrong because the passage explicitly states that it is the tumor cells that express the highest levels of EGFR. B says kidney cells bind more SC44. This option is also wrong because SC44 does not bind EGFR. So option C is correct because kidneys process the tracer to clear it from the body. Kidneys filter blood, removing waste, so it makes sense that the tracer levels would stay higher in the kidneys. Option D states kidneys would have a higher affinity for the chelator, the CHXA DTPA. This statement is not mentioned in the passage. When you see a question like this, so don't overthink the details and just stay focused on what the passage tells you. Apply what you know about basic science and use the process of elimination to find the right answer. So the right answer to this question is answer choice C. Let's move on to question number 4. Question number 4 was a bit long, and it says in a follow up experiment, scientists used different isotopes of scandium that undergoes alpha decay. They repeated the procedure to perform a PET scan, successfully binding this new scandium isotope to the Fab region of cetuximab and the CHXA DTPA chelator to form the same three component tracer complex. However, After injecting this tracer into a patient, no binding of the Fab region to its target receptor was detected. Which of the following provides the most reasonable explanation for this observation? Remember from the second sentence of the passage that a PET scanner detects gamma photons released when a positron annihilates with an electron? That means PET detection relies on positron emission, not alpha decay. So in this case, the new isotope of scandium undergoes alpha decay. So it produces a helium 4 nucleus, it does not produce a positron. So since no positron is released, no annihilation takes place with an electron and no gamma photons are produced. So the PET scanner cannot detect the tracer. This matches answer choice D. So the answer choice D is the correct answer to this question. This question shows why it is important to analyze the passage as we did. Remember when we said that the second sentence of the passage could be important? Here's where that pays off. Always note science facts, relationships, or comparisons. And also note for any repeated ideas. They often show up later in questions. So let's move on to the final question of this video, number 5. Number 5 says within liver tissue, what type of nuclear decay does scandium 44 undergo that allow it to be detected by a PET scanner? This question is actually asking how does scandium 44 produce a signal that the PET scanner can detect? The passage tells us that the PET scanner detects gamma photons from the annihilation of a positron with an electron. The name positron emission tomography also hints at that same answer. So scandium 44 undergoes beta positive or beta plus decay, producing a positron that annihilates with an electron and it emits a gamma photon, which is detectable by a PET scanner. So the correct answer to this question is the answer choice A. So with that said, this concludes our video. Great job making it to the end of this lesson in this video. We went over one of the most high yield MCAT physics and chemistry topics, which is called the radioactive decay half-life. We didn't just stop at definitions, we applied the concept to real MCAT style passage and worked through it step by step. Remember, the MCAT tests how well you apply what you know to new situations and scenarios. So, as long as you understand the concepts behind half life radioactive decay, you can reason through any problem the test throws at you. Keep practicing and remind yourself that you already have the tools to succeed. Thank you for watching and keep up the amazing work.